There are lots of statements in A-level physics that are almost guaranteed to give you marks. In this video, we're going to have a look at loads of these from different parts of the specification, often asked to describe and explain the motion of an object. If that happens, the first thing that I need you guys to do is to bullet point the number of marks available as answers. This will ensure that you won't miss any marks, because if you just write two statements and there are 4 marks available, you are unlikely to score 4 marks. The second thing that I would like you to do is to think what forces are acting on the object. For instance, if the velocity time graph is a straight line through the origin, this would mean that the acceleration is constant, and this means that there would be a constant force acting on the object. Provide as much detail as possible. If the acceleration is indeed constant, we need to mention it. If the acceleration is increasing or decreasing, we also need to mention that. In projectile motion, we're very often asked to describe and explain how the horizontal or the vertical components of the acceleration vary. In the horizontal direction, there is no horizontal forces. We only have the force of the weight, which is acting straight downwards. Therefore, there is no acceleration in the horizontal direction, and the velocity is constant. In the y direction though, in the absence of air resistance, the only force that acts is the force due to gravity. This makes the vertical component of the velocity decrease as soon as the projectile is fired at a constant rate, reach 0, and then the velocity starts increasing yet again at a constant rate. Talking about projectiles, if we needed to work out the maximum height of an object, typically you want to use this Farad equation that v squared is equal to u squared plus 2as. Remember, at the maximum height, the final speed v is equal to 0 in the y direction, meaning this here will be equal to u squared, and then the acceleration will be negative 9.81, let's call it negative g, meaning that u squared will be equal to 2gs, and then the maximum height, in this case s, will just be equal to u squared divided by 2g. If drag is present in projectile motion, this will decrease the horizontal component, and hence it will decrease the time that the projectile spends in the air. If Archimedes Principle is in your specification, you can solve most problems mathematically by thinking that if we have an object that is submerged, the upthrust acting on the object, let's call that U, is equal to the weight of the fluid that's been displaced. So this here will be equal to the mass of the fluid, let's give it a little subscript for F, multiplied by G. Now, in fluids in general, it is really useful to represent this in terms of the density of the fluid multiplied by its volume and then multiplied by G. Often this volume V, depending on the shape, can be expressed as the cross-sectional area multiplied by the height multiplied by G, but this is crucially the density of the fluid. You also have the weight, which is mg, where this here is the mass of the object, which is acting downwards. If the upthrust is bigger than this, the object will start to rise. If they're exactly equal, the object will float, and if the weight vector is bigger, the object will be sinking. If you have an object which is placed at a height h, and you're wondering, you need to calculate at what speed it actually hits the ground, it is probably easiest just to use conservation of energy, so you can just say a half mv squared is equal to mgh, the masses just cancel, giving me that the speed v will be square root of 2gh in the absence of air resistance. And this can save us sometimes quite a lot of work with these Farad equations. If we have springs in series and springs in parallel, the rules for adding the spring constants are kind of the same as adding resistors, but opposite. In series, k total is 1 over k1 plus 1 over k2, all of this raised to the power of -1, and then in parallel, the spring constants are just added. This is because in series, they actually share the same force, and the actual extensions are added, giving us this rule, and here the extensions are the same, so they cancel out, but the actual force is shared between the two springs. In a force against extension graph, the area underneath the graph is equal to the work done. On the other hand, in a stress against strain graph, the area is equal to the work done per unit volume. Why is this? Well, let's consider this case in particular. So the area will be a half the base, which is the strain, multiplied by the height, which is the stress. Okay, so this here will be a half x over L, where x is the extension, L is the original length, multiplied by the stress, which is F divided by the cross-sectional area. That's the definition of stress. Okay, well, a half Fx, this is just the work done. Length multiplied by the cross-sectional area, this is just the volume of whatever we're extending. We need to know the stress and strain graphs for a few different materials. Number one, ductile. So initially we have the elastic region up to the elastic limit when a material will return to its original shape once the force is removed. Beyond the elastic limit, we have the plastic region in which the material will not return to its original shape after the force is removed. If you're doing Edexcel in particular, you also need to know about the yield point, which is this point over here, which is a point at which a large amount of strain / extension occurs for the same amount of stress. All exam boards need to know about the ultimate tensile strength, which is the maximum stress that a material can withstand before its breaking point. You also have a brittle material in which you have some amount of extension, which is originally linear, and then the material just reaches its breaking point without any limit of proportionality. It just breaks. With rubber, the situation is a little bit more interesting. So we have a loading curve where we apply the stress, and we have an unloading curve. Now, some of the energy is transferred onto the rubber, and we can work out the amount of energy per unit volume from this graph, or if it's a force against extension graph, it will just be the area, by the differences in the two areas. We can estimate how much energy has gone into heating up the rubber. Imagine that you have an object which is initially at rest, u is equal to 0, let's say, and then we apply a force onto this for a time t, such as this curve here, and then the object starts to accelerate. We can work out its final speed using the area of this graph. Why is that? Because the area of this graph is equal to the impulse. Now remember, the impulse is defined as the average force multiplied by the time that it acts, in other words F delta t, and this is equal to the change of momentum. If the object has started from rest, then F delta t, which is the area, will just be equal to mv take away mu, but this term here is equal to 0. That often happens in questions, but it doesn't have to occur. Just know that the area is equal to the change of momentum, not the final momentum in general. Okay, now in this case our initial speed was equal to 0, so therefore to work out the final speed, this is just equal to F delta t divided by the mass. Talking about change of momentum, imagine that I have a particle that is going this way with a positive speed of, let's say, v. Then it rebounds elastically, and afterwards it is moving with a speed in the opposite direction, which is v, or with a magnitude v, but we need to really be using the negative sign here. What is the change of momentum in that particle? So if it's gone from a speed of +5 to -5, then the change of speed is actually going to be -10 meters per second. So mathematically we can say that the change of momentum in this particle will be equal to final speed, which is negative mv, and then take away the initial speed, which was just equal to mv, which is going to give me -2mv for the change of momentum. Please note that the answer will be positive if we've taken this to be negative and this to be positive, but that's the case in all of physics. Remember that Kirchhoff's first law states that the sum of the currents entering a junction is equal to the sum of the currents exiting a junction, and this is a statement of conservation of charge. Kirchhoff's second law states that the sum of the EMFs is equal to the sum of the PDs in a closed loop in a circuit, and this is a statement of conservation of energy. If you're ever feeling a little bit stuck on an electricity question and you need to work out the voltage or the work done or the energy transferred, you may want to use this equation that voltage or potential difference is equal to the work done per unit charge. From this equation, the actual definitions of EMF and potential difference arise. So EMF is the amount of energy transferred from other sources, such as chemical, to electrical per unit charge. Potential difference is the amount of energy transferred from electrical to other sources, such as heat, per unit charge. So potential divider questions typically have to be solved by looking at what's happening at the fixed resistor. So we have a thermistor over here, and let's say that the temperature increases. Well, if the temperature increases, the resistance of the thermistor will actually decrease. So always think, first of all, what's happening to the resistance in the circuit. So if the temperature goes up, the resistance in the circuit goes down. Because of that, the current in the circuit will increase. Now, if the current in the circuit increases, there is a fixed amount of resistance across here. So the PD across the fixed resistor will be equal to IR fixed. And if the current has increased, this means that this potential difference here would have increased. If this potential difference here has increased, this means that the voltage across the thermistor has decreased. So to recap, in potential divider questions, start from the resistance of the circuit. Does it go up or down? The current will do the opposite. Then look at the fixed resistor. If the current goes up, the voltage across the fixed resistor will also go up. And then afterwards, look at your component. In this case, the thermistor, or the voltage across the thermistor, will go down. They need to add up to a fixed amount. This can be a little bit tricky to understand, so plugging in numbers can sometimes help you in those situations. So let's say that this one here was 10, and initially there were 5, and there were 5, but if this one here increased to 6 volts, then this one here will have to decrease to 4 volts because they need to add up to 10. Always think of internal resistance as an extra resistor in the circuit which is in series with the actual cell. Now, we can have situations in which we have cells which are connected, let's say, in parallel, and if internal resistance is not ignored, we will draw it like such as part of the circuit. And I always add this to a diagram to help me think of the actual problem. If that's the case, the internal resistances are, if they're in parallel, will just be added up such as this, just as normal resistors in parallel. If they're connected in series, on the other hand, they're just going to be added as normal. Sometimes they will try and trick us in questions by not explicitly telling us to consider internal resistance. Look for clues in the question. If it says something such, if it says this is a practical circuit or this is a real-world laboratory circuit, something of that nature, this is a clue to you that you need to consider internal resistance. Or if the voltage is doing something that it shouldn't be doing, the answer to an explain question might be internal resistance. If you have a graph of the terminal PD across the current, we can express the gradient of this graph using the fact that the EMF across a circuit is equal to the terminal PD plus the amount of lost volts. Okay, well, this here will be equal to the terminal PD plus IR. Let's just say that V will be equal to minus R times I plus E, just with a little bit of clever rearranging. And this would mean that our gradient M will be the negative of the internal resistance, and my y-intercept will be equal to the EMF. Very often in something like a multiple choice question, they might ask us what is the EMF, and it's typically just the y-intercept. In waves, if you have to state the principle of superposition, you have to refer to the displacement, stating that when two waves interact, the resultant displacement is equal to the sum of the individual displacements. You shouldn't lose marks on orders of magnitude on the electromagnetic spectrum. In other words, if they give you a wavelength or a frequency, what part of the EM spectrum would that correspond? Here are a few tips. Always remember that microwaves are somewhere around a few centimeters. X-rays are of the order of 10 to the minus 10, maybe up to 10 to the power of minus 12. Everything much smaller than this is bound to be a gamma ray. Visible light is from about 400 to somewhere around 700 nanometers, with the shorter waves being blue and the longer wavelengths being red. Once you know a few of these and you simply know the order of the EM spectrum, you typically can solve all the questions simply by approximating. You need to understand how the critical angle in optics is derived and how it works. Typically in A level, you're given this equation in the formula sheet that the sine of the critical angle is 1 over n. Now, this equation presumes that we're going from a substance of a high refractive index n, such as glass, into air, which has a refractive index of 1. But if we're not going from air, if we're going from a substance, let's say N1, to a substance N2, this equation here will change. So the way it works is that we want an angle such as an incoming ray from N1 will not go into N2, but it will be trapped at the boundary. So we're going to use Snell's law that N sine theta 1 is equal to N2 sine theta 2. When the angle theta 1 is equal to the critical angle, the ray becomes trapped along the boundary, meaning that sine theta 2, well, meaning that theta 2 will just be equal to 90 degrees. So this here will be N2 sine of 90, which is just 1, so we don't really need to write this. This means that sine of the critical angle will be equal to N2 divided by N1, and this here is an equation that we would need to use. Mathematically, it also tells us that N2 has to be smaller than N1 for this sine function to be defined within this region. In quantum physics explanations, many students use statements such as one-to-one interactions without further explaining and possibly losing some marks. So how does the photoelectric effect prove the particle nature of light? Well, first of all, according to the wave classical theory, even if we used visible light, then after some time we should get enough energy build up and we should get electrons being released. However, this is not what happens. If we use visible light, no matter how intense, intensity in this case just simply means the number of photons really, no ejections of electrons occur. On the other hand, according to classical theory, if we used UV light, then it would take some time for the energy to build up. But in practice, the emission of electrons is virtually instantaneous as soon as we switch on the UV light. This proves that the energy arrives in packets or quanta of photons of energy equal to HF, and there's a one-to-one interaction, meaning that with visible light we cannot get, let's say, 1 billion photons interacting with a single electron and then emitting it. That doesn't happen. Talking about quantum, it's worth revising the definition of the work function, that is the minimum amount of energy required to release an electron from the surface of the metal. Now, why is it a minimum energy? Because in practice, most electrons require more energy than the work function in order to be released. Practice doing some de Broglie wavelength equation problems. So the de Broglie wavelength of a particle is equal to Planck's constant divided by P, which is the momentum. Another way to write this is h divided by mv. Now, in some cases, we can solve the de Broglie wavelength problems a lot easier if we just remember that energy or kinetic energy is expressed in terms of the momentum as p squared over 2m. Why is that? Well, we can actually see why that is. So p squared is m squared v squared over 2m. So this is just equal to a half mv squared. You don't really need to know that formula, but it's very useful in multiple situations. So let's say if we were to change the energy, then we can work out the change of momentum pretty much straight away, and then we could take that and then plug that into here to work out the wavelength. And in many cases this is a lot easier. In thermal physics, think about the amount of substance as exactly around 6.02 times 10 to the power of 23 particles. If we're given the molar mass, that's the mass of that many particles. Typically we have to figure out the number of particles, and as soon as I'm given the molar mass, I typically just write down number of particles is mass over molar mass times by Avogadro's number. Remember the assumptions of the kinetic theory. They do tend to come up quite often. Sometimes we're asked to define the internal energy of a substance. So this is typically given the symbol U, and that's defined as the sum of all of the kinetic energies plus all of the potential energies of the particles of that substance. We can also say that it's the sum of the randomly distributed kinetic energies and potential energies of all the particles in the substance, but the word particle or atom or molecule is actually typically underlined in the mark schemes, so we have to use that. Define absolute zero in terms of the minimum energy. The absolute zero temperature is a state at which the total internal energy of a system is a minimum. This happens when the kinetic energy starts tending towards zero. It never actually reaches there, but it starts tending towards there. And even at absolute zero, there's still some potential energy left within the molecules. That's why the internal energy is not zero at absolute zero temperature. Why is an object performing circular motion? The answer is always the same. In order for an object to perform circular motion, be it a mechanical example or a particle that is moving in an EM field, there is always a force which is acting towards the center of rotation, and that force is perpendicular to the velocities, perpendicular to the displacement, and there is no work done in this case. Because of that, the speed does not actually change. The velocity, on the other hand, does change because the direction is changing. So here's pointing this way, here is pointing this way, here is pointing this way, and so on and so forth. In order for an object to be performing simple harmonic motions, two conditions need to be met. The acceleration needs to be proportional to the displacement, and this is shown by this graph being a straight line through the origin. Number two, the acceleration needs to be directed towards the equilibrium position, and this is shown in this graph by this negative gradient. If the acceleration is positive, the displacement is negative, and vice versa. If you were to use the displacement equations for simple harmonic motion, your calculator needs to be in radian mode. Please note that these equations are essentially functions of time. In other words, this here is the displacement at time t, and so is this one. Very often we have to write them. Let's take the cos equation, for instance, as a cosine. Now omega is 2 pi over t multiplied by t. This capital T here is the time period, which is typically fixed for a system, and this here is the displacement x at time t. Natural frequency is defined as the frequency at which an object will oscillate after an initial disturbance. Resonance occurs when the driving frequency matches the natural frequency, and then the amplitude reaches a maximum. At this point as well, maximum energy transfer occurs from the driver of the oscillation to whatever is being oscillated. In practice, the amplitude against driving frequency graph will kind of look something like this, with a sharp peak centered at f0. If we were to introduce some damping into the system, then the peak gets shifted to the left. The actual curve becomes thinner as well, and this here is the new natural frequency. Let's call it f2, and this is with damping. The actual amplitude becomes smaller. This does not affect the time period because, remember, in simple harmonic motion, the time period is independent of the amplitude. In gravitational fields, it is best to define gravitational field strength as the amount of force per unit mass that an object will experience in a gravitational field. State and also explain questions are typically grounded in mathematics. For instance, if we have to state Newton's law of universal gravitational attraction, we can say that the gravitational force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. Please note that if we're talking about large objects that are not point masses, for instance planets, we have to take into consideration the radii of the two planets. So if we have an object which is orbiting, let's say we have a satellite in a circular orbit, the total energy is going to be negative if it's actually in orbit and it's not moving, and it's going to be given by the kinetic energy plus the gravitational potential energy, which is actually negative, so minus gmm over r. So this here is kinetic energy plus the negative potential energy. Once those two are equal and the total energy is zero, the object will start to escape from that field, and we're going to get the escape velocity. So in other words, a half mv squared, take away gmm over r has to be equal to 0. We set those two equal to one another. This is where this equation actually comes from. So what do we get for the escape velocity? We get that v squared will be equal to 2gm over r, and we can just square root this expression for the escape velocity. In astrophysics, very often we have to use Wien's law that the peak wavelength is inversely proportional to the temperature. The best way to typically write this is using proportionality. We'll typically be comparing a couple of different stars. So I always just write lambda 1 times T1 is equal to lambda 2 times T2. Typically we're given 3 of those, then we have to work out one of these, but not exclusively. We have to read the question as well. Let's consider the evidence for the Big Bang Theory. One of the main pieces of evidence for the Big Bang Theory is the redshift of distant galaxies and how they all appear to be moving away from us, as stated in Hubble's law, which states that the velocity of a distant galaxy is proportional to the distance from the Earth. Please note that you have to use the word distant galaxy because some close by galaxies, such as Andromeda, are actually moving towards us. Another evidence for the Big Bang Theory is the cosmic microwave background radiation. It corresponds to a temperature of 2.7 Kelvin. This means that if I was to put a thermometer in outer space, the radiation will heat it up a little bit just above absolute zero. It is uniform in all directions, and it started off as gamma rays in the early universe and has since been redshifted to the microwave spectrum. It was theoretically predicted and then observed in the 1960s, confirming the theories for the Big Bang. Moving on to capacitors, the energy of a capacitor is given by a half QV. This is an equation which is given in the specification, but sometimes a question might trick you. How does the energy depend on the voltage? Remember that Q actually depends on the voltage because Q is equal to CV, so the energy is equal to a half CV squared, meaning that the energy stored in a capacitor is proportional to the square of the voltage. We also add capacitors in the opposite ways to resistors. So in series, they're added by this expression, and in parallel, they're just added by this expression. The time constant of a capacitor is defined as the time taken for the PD across the capacitor to fall to around 37% of its initial value during discharging. How does that work? Well, if we said V is equal to V naught e to the power of minus CR, we get minus CR over CR, meaning that V will be equal to V naught e to the power of minus 1. And this factor 1 over E is around 37%. So the mathematical expression for the time constant is C times R. Very often we're given graphs such as these ones in which, let's say that we're given a graph of the voltage against time in seconds, and it drops from T is equal and it drops from, let's say, 10 volts to 3.7 volts in around 7 seconds. Well, because it has dropped to 37% of its initial value, this means that the time constant is going to be 7 seconds, and if we're given the resistance or the capacitance, we can work out the other really easily without actually having to use the exponential decay equation. Sometimes in capacitors, it's useful to think about the half-life of a capacitor. So V over V naught will be equal to e to the minus t over CR. Well, if that's the case, this here will be a fraction of a half, which will be equal to e to the minus t over CR. Let's take the ln of both sides, so we get ln of a half. The ln and the e are going to cancel out. We're left with minus t over CR. The minus sign will just flip the ln, so we get ln of 2 is equal to the half-life over CR, meaning that the half-life of a capacitor is equal to ln of 2 multiplied by CR, and this is exactly the same as the half-life in radioactivity, but kind of applied to capacitors, and this could be a nice little shortcut to some problems. If you're asked to define the unit, always define a unit in terms of other units. For instance, because capacitance is equal to charge over voltage, we can say that 1 farad will be equal to 1 coulomb of charge stored in per 1 volt. On the other hand, the definition of capacitance will be the amount of charge stored per unit volt. And that defines a quantity in terms of other quantities, and this defines a unit in terms of other units. If the charging of a capacitor is in your specification, it's really useful to understand what's happening in the circuit during charging. So let's say this capacitor is uncharged initially, and then we flip the switch and then we start charging it. The EMF in the circuit is V naught, this here is VC, and this here will be equal to the voltage across the resistor. So because of Kirchhoff's second law, V naught will be equal to VR plus the voltage across the capacitor. As the capacitor is charging, the voltage across it will start to increase, and this one here will actually experience an exponential decay. So V naught will actually be equal to V naught e to the minus t over CR. So the moment it starts charging, the voltage across the resistor is actually equal to the EMF, because this one here will be equal to 0. Okay. So plus VC, we can rearrange for the voltage across the capacitor, and what we're going to get is V naught with a little bit of rearranging 1 minus e to the minus t over CR. And this is an equation that we only use for the charging of a capacitor. In nuclear physics, the binding energy is defined as the minimum energy required to separate the nucleus into its constituents. Be confident in explaining the features of the binding energy per nucleon curve against the nucleon number. In both nuclear fission and nuclear fusion, we're going to a region of higher binding energy per nucleon. In both cases, actual mass is converted to binding energy, and this is where the energy actually comes from the conversion of mass. Nuclear fusion gives a relative higher amount of binding energy per nucleon. As you can see, the rate of change of binding energy per nucleon is steeper in this portion of the graph. Let's talk about radioactivity. Radioactive decay is both spontaneous and random. The word spontaneous means that we cannot induce it with external factors such as pressure or temperature, etc. Random means that we absolutely cannot predict when nuclear decay will occur for an individual nuclei. If you're a radioactive nuclei in a substance, you could decay in an instant or in a million years. There's no way to predict that for an individual nuclei. In terms of equations, there's a few main ones that we need to know. So the activity is equal to the number of particles that have decayed per unit time. The activity is also equal to lambda multiplied by n, where n is the amount of undecayed nuclei. But what is lambda in this case? Well, the decay constant. So the decay constant is defined as the probability that a single nucleus will decay per unit time. Because of that, it has units of time to the power of -1, such as hours to the power of -1 or seconds to the power of -1. We can derive the half-life equation in a very similar way to the capacitor derivation, and what we get is that the half-life is equal to the natural log of 2 divided by the decay constant. In radioactivity questions, if we have the decay constant, we can immediately calculate the half-life, and normally when I'm reading a question and I notice that one of them is given, I immediately just calculate the other because I know I'll probably be using that later in the question. Another graph that we very often get is the ln of the activity against time. Now this curve will typically have a negative gradient, will look something like this. Well, let's perform a bit of y equals mx plus c analysis starting from this. So I'm going to go ln of a over a naught is equal to ln of e to the minus lambda t. Okay, so ln of a will be equal to minus lambda t, and then plus ln of a naught, because ln of a over a naught is equal to ln of a take away ln of a naught, and I've just brought this to this side. Okay, so ln of then I'm basically ready to apply y equals mx plus c analysis. So y is going to be equal to mx plus c. This here will be ln of a naught, and you can see that my gradient will be the negative of the decay constant. And then we can use this to work out the half-life directly from this graph. While this video was filled with loads of very useful things, they're definitely not enough, and the list is not exhaustive. It's precisely why you should have a look at this video next, in which I go over even more of these to help you get the maximum grade in the exam.